So today's lesson is going to be on hybridization. And so let's look at hybridization and see if we can't figure out what it is and what it means. All right, so to look at hybridization, let's start with carbon. And if I wanted to draw the electron configuration for carbon, it is 1s2, 2s2, 2p2. All right, carbon ends in 2p2. So carbon has 4 valence electrons. 2 plus 2 is 4. So if we were to draw our valence electrons in terms of energy, the 2s has 2 electrons in it, and it has less energy than the 2p. So the 2p has more energy, and the 2p has 2 valence electrons. So hybridization is when orbitals overlap, and they overlap in such a way that energy is minimized. So what we have is an overlapping between our s and our p orbital. And because they overlap, this electron from the s will actually move into the p. And now if I take one away and put it in the p, my p is now half filled, and so carbon is more happy, right? Because remember, a half filled is better than a non-half filled. And what we end up with is some sort of energy that is halfway in between, okay? So I have 1 electron in the s, and I have, this is the 2s, and I have the 2p. So I have an electron here, this is an electron, and then 1 moved up. So now what I end up with is 4 unpaired electrons. And this is why carbon can form 4 bonds. Look at methane, for example, CH4, carbon tetrahydride. This is why carbon can form 4 bonds, because it has 4 spots for electrons to come in and be shared. So in terms of the hybridization of carbon, if you remember, the S is spherical, and the P has this shape right here. So if you remember, the S, P, D, and the F, they all have different shapes. All right. So if we were to draw the hybridization of carbon, it has the 1s, which is a spherical, and then we have the 2s, and overlapping the 2s is the 2p, and there are 3 different orbitals, so I have to draw 3 different p's. So here's my hybridization of carbon. So we have an overlapping of the 2s and the 2p. All right, so let's do one more example. Let's do NH3, ammonia. Now, if you were to draw ammonia, draw the electron configuration, draw the structure for ammonia, and you find that ammonia has 5 plus 3 is 8 electrons. Okay, and so 2, 4, 6 plus ammonia has a lone pair. All right, so let's see, where does this lone pair come in terms of hybridization? Nitrogen has 5 valence electrons. So if we were to draw the valence electrons for nitrogen, it has 2 in the 2s. Here's nitrogen, 2 in the 2s and 3 in the 2p. So what we find when we have an overlapping of the S and the P, an electron from the S comes in and joins in the 2p. And I end up with something that has an energy in the middle of both the 2s and the 2p. So not as high as the 2p, but not quite as low as the 2s. So I have one electron, one electron, one electron, and then these are our lone pair right here that we see on the nitrogen. All right. And then it has 3 spaces for hydrogen, a space for the 2s, the 2p, and another 2p. There are the 3 hydrogen bonds. So the way to do our hybridization basically is we have to add up. Okay, so let's look at our chart in terms of hybridization. These are sp, and these are sp2, and these are sp3. All right, what does that mean? I have 4 things around the central atom. 3 plus 1 is 4. I have 3 things around the central atom. 2 plus 1 is 3. I have 2 things around the central, or 2 things here, so sp. So the linears are sp. So essentially, how many things are around the central atom? And from there, we have to make their number match however many things are around the central atom. All right. We only have 1 orbital in the s. The p can have 3 orbitals, so 3 plus 1 is 4. I have 5 things around the central atom, so I now have to go into the d subshell. All right. So 3 plus 1 is 4, plus 1 is 5. If I have 6 things around the central atom, my s can hold 1 orbital, my p has 3 orbitals, and my d, I have 6 things around it, so 3 plus 1 is 4, so that needs to be a d2 in order to give me 6 total. 3 plus 2 is 5, plus 1 is 6.